Hello friends, welcome back to this online certification course on watershed hydrology. I am Rajendra Singh, professor in the Department of Agriculture and Food Engineering at Indian Institute of Technology, Kharagpur. We are in module 3, this is lecture 2 and this is entitled Streamflow Measurement Part 1. And in this lecture, we will discuss about streamflow measurement, measurement of stage and measurement of flow velocity. Now, already we have seen stream flow process in the previous lecture and we know that stream flow is flow occurring in cross section of a river stream of a water course. So, stream flow measurement is the process of quantifying the magnitude of water, usually in discharge units, say cubic meter per second or cubic, moving within rivers, streams or other water courses. So, we saw that at any cross section, if you measure the flow, that is stream flow, and if you quantify that in terms of discharge units, say cubic meter per second or cubic, that is nothing but measuring discharge or stream flow measurement. Basically the science and practice of stream flow measurement is referred to as hydrometry. So, that means anytime we are trying to quantify or measure flow, we are dealing with hydrometry. And the accurate measurement of stream flow is vital for various purposes such as managing water resources, monitoring environmental conditions, predicting floods and conducting hydrological research. So, obviously, if you want to manage water resource of a region, a place or a country, then obviously you must know how much water is available. And of course, because streams and rivers, they carry most of the water. So, obviously, you have to have a good idea about how much flow is taking place in those streams, and that can only be known through stream flow measurement. And of course, as you remember in the initial lecture, introductory lecture, I also gave you water resources of the country, because we must know how much water is available, and then only we can think about managing it. We can predict floods in case of higher flows, or we can monitor environmental conditions based on if flows are low, and of course, for carrying any kind of hydrological research, you require stream flow. Now, several direct and indirect methods are available for stream flow measurement. Like direct stream flow measurements include area velocity method, electromagnetic method, dilution techniques and ultrasonic method, where indirect stream flow measurement methods include use of hydraulic structures such as weirs, flumes, gated structures, and of course, the slope area method. And during our today's lecture and next 2 more lectures, we will talk about various methods, all these various methods of finding out stream or measuring stream flow. Now, though there are multiple direct and indirect methods of stream flow measurement, but most commonly adopted procedure worldwide for determining stream flow is through stream gauging. So, what happens is that in this it is a 2-step procedure, and first what we do is we develop a stage discharge relationship for a given stream by a series of careful measurements of the discharge and the corresponding water surface elevation or stage. So, what is done is that elevation versus discharge, we try to develop a relationship, and that is a stage discharge relationship. As I already mentioned that of course, such data can come only from measurements, that is measurements of stream flow at various elevations with respect to a datum, and then you have the relationship. Next, the stream gauge stage is gauged routinely in a relatively inexpensive manner, and subsequently the discharge is estimated using the previously established stage relationship. So, first thing what we do, we develop this relationship, stage discharge relationship, and then we measure only the stage or elevation, and then knowing the stage or elevation as shown here, if we know the stage, we can find out how much flow is taking place in the stream. And the method is popular because measuring stream flow directly is a resource intensive and it requires huge investment of time and money. So, that means if you want to measure it, many of the methods we have seen, if you want to measure stream flow, then obviously it's a very expensive procedure because it involves investment on time and money, and that is why this inexpensive way of just measuring the stage and then using the stage discharge relationship is most popular or most commonly adopted procedure worldwide for estimating discharge. Now, as we have seen that stage measurement is a major activity in case of stream flow measurement, and the stage could be measured using either manual or automatic gauges. The manual gauges could be of staff gauge type or wire gauge, whereas automatic stage recorder could be float gauge recorder or bubble gauge, and we will see one by one. Now, coming to staff gauge, it consists of a long vertical marked ruler made of wood, metal or fiberglass. It may be flat or round in the shape. As you can see here, this is a just a ruler with marks marks made on it, and it could be of wood, metal or fiberglass, and it could be round or flat. So, it is very similar to the ruler or scale which we use in our day to life for measuring, and we know that scale is also could be is also of wood or metal or fiberglass. We have used all those types in our day to day life, and the units of measurement may be feet, meters, inches or centimeters. You remember in our typical rulers which we use, we have inches and feet and centimeters and meters. So, similar procedure could be similar scale could be made here in the staff gauge. These are installed at a specific location in the stream, usually anchored to a structure like a bridge, pier or post securely placed in water. So, of course, they should be very stable for correct measurement of the stage. So, that is why they are always anchored to a stable structure like bridge or piers, and if the depth of water is not too much, then of course, there could be a post which could be securely placed in water, and then this scale could be fixed. And they are set up such that the 0 mark align with water surface at a defined reference point. Of course, because we have already a stage discharge relationship which we intend to use after measuring this stage. So, obviously, the reference point or the datum which we use here is very important, because that datum should correspond to the datum that has been used for developing the stage discharge relationship. And of course, when you cross major bridges, you might have noticed that several times the walls of the bridge itself, they are marked for different stages or water levels. So, and also in news during flood times, you in the news or newspapers or in the television news, you come across the term that but so and so river is flowing above the danger mark, and many a times we can visualize that danger mark near a river, near a bridge or a pier, because that we can see because the scales are marked on the wall there. Then other type of non-recording gauge could be a wire gauge, which comprises a drum wound with a graduated wire cable with a weight affixed to the free end. So, you can see here there is a drum here on which this wire cable is wound, and of course, at the loose end we affix a weight. And a mechanical counter measures the rotation of the drum, which is proportional to the length of the cable. So, either the measurement could be in two ways. One could be the cable itself could have measurements, or the rotation of the drum also could be measured in order to know how much cable has been lowered for reaching the water level. For measuring the stage, the water surface elevation, the weight is lowered to touch the water surface, causing a slight ripple. So, we simply lower this cable, and then when it touches the ground water surface, just touches and there is a ripple, then we stop, and that gives us the water surface elevation or the stage, and that of course we have to use the datum which we have used earlier as mentioned. Then we can talk about automatic float gauge recorder, which is the most commonly used automatic stage level recorder. And basically, a float gauge recorder consists of a float housed in a steering wheel. So, of course, a major requirement of fixing up or installing a automated float gauge recorder is that we should have a steering basin constructed just near the stream. This steering wheel protects the float from debris, besides eliminating the wind effect on the stage measurement. So, obviously what happens is that there are inlet pipes from the stream just at the bottom of steering wheel and little up also, and in such a way that the water level in the stream and in the steering wheel, they are maintained at the same level. And of course, because it is a protected area, so debris etc. cannot enter this steering wheel. Also, if we make the measurement outside, then of course, the surface of the water will be affected because of winds and all, but because steering wheel it is protected, so there is no wind effect. So, we get the correct measurement of the stage. The float is connected to one end of a cable passing over a pulley connected to a recorder, while the other end of the cable holds a counterweight. So, here you can see this is basically a pulley kind of thing, and this is your float, and the other side, the free end of this cable has a counterweight. The recorder includes a pen recording on a daily or weekly chart mounted on a drum driven by a clockwork mechanism. So, of course, linked to this pulley is a recording mechanism, very similar to what we discussed in a recording type of rain gauge, say siphon type of rain gauge or weighing bucket type of rain gauge. So, what happens that whenever the water level changes, this float level will change, and that will make a movement in the pen, and that will make a recording. So, the movement of float due to the rise or fall in the water level causes pulley movement, which triggers the pen movement on the chart, thus recording the changes in the stage. So, as we saw in the case of rain gauges, that there is a drum on which the chart is placed, and which basically runs based on a clockwork mechanism, that is along the clock. So, obviously, when there is no change in water level, we will get a horizontal line, but whenever there is a change in the water level in the stream water level or water level in the steering wheel, here the float will rise or fall, and that will be recorded by the pen movement. Although the float gauge recorder ensures precise stage measurement, its installation is expensive, and that is primarily because we require this steering wheel. So, steering wheel forms the most expensive part, besides the equipment of course of this installation. The other automatic measurement is through bubble gauge, which involves channeling a compressed gas, typically nitrogen, through a tube. This gas is then released slowly into the stream via an orifice fixed at the specific location in the stream underwater. So, as you can see here, this is a chamber and a gas cylinder here, and through a tube, this is the orifice line. This orifice is placed at the bottom under the water. So, this is the orifice, and then gas is released into the stream through this gas cylinder. The resulting gas pressure in the tube reflects the combined pressure and elevation heads at the orifice, that is the height of water over the orifice is reflected in the pressure measured by either a manometer or a pressure transducer. So, here linked to a gas cylinder, we have a manometer or pressure transducer that records the pressure, and that pressure will include not only the pressure of the gas, but also the water level changes. As the depth of water above the orifice increases, more pressure is required to push the gas bubbles through the tube. So, that means any change in the water level will change the pressure on the gas cylinder for releasing the gas here, and that will be recorded by the manometer or the pressure transducer. The bubble gauge offers certain advantage over the float gauge recorder, such as it does not require the costly steering wheel. In fact, the pressure measurement assembly may be kept far away from the stream. So, as we saw in the case of automatic stage level recorder, we have to have a steering wheel, and because we know that water level is maintained at the same level in the stream as well in the steering wheel. So, obviously, that cannot be too far off from the stream, because there is the pipes are inserted from the stream to take the water to steering wheel. But here in this case, it is only a orifice line or a simple tube that is taking gas to this orifice below the water, below the stream level, and that is why this particular arrangement could be far off, because only a pipe has to go. So, that is why it is much less expensive as compared to a stage level recorder. But of course, coming back, we have already seen that the most commonly used way is to use this rating curve, and this rating curve is nothing but the stage discharge relationship developed and used for estimating discharge. So, that earlier we talked about the elevation discharge relationship which we developed, and that is referred to as rating curve. So, basically, once we have a rating curve for a specific stream location, then if we measure the stage using either the manual, that is a stab gauge, or the wire gauge, or the automatic stage level recorder, or the bubble gauge, if you know the stage, then of course, that stage can be converted into discharge quite easily. The rating curve for a specific stream location is developed by making successive stream flow measurements at many stream stages to define and maintain a discharge stage relationship. That we already discussed earlier also, that of course, we have to conduct experiments or measure flow at different stages in order to be able to develop this stage discharge curve or rating curve. And it is crucial because it allows the use of the stream stage, which is easily determined. So, just now we discussed that we measure the stage, and using the rating curve we can find out what is the stream flow in a given river. And the problem is that the discharge stream may be affected due to changes in the flow characteristics, owing to change in the channel due to dredging, weed growth, or sedimentation, that is both aggradation or degradation in alluvial channels. So, obviously, we just now discussed that what we do is carry experiment at a particular cross section of the river in order to develop the stage discharge relationship. But if the cross section of the river or stream gets affected, so for example, if there is a sand mining dredging, so obviously the cross section will go up. If there is a weed growth, the cross section will reduce. And similarly, due to sedimentation, whether it is aggradation or degradation, aggradation means the silt is getting deposited at that cross section, and degradation means the silt is being taken away from that cross section. So, there will be cross sectional changes, and if that happens, then obviously the rating curve which we have developed, that will be affected. And in such cases, rating curves may need to be updated periodically, that is continuous monitoring and occasional recalibration may be needed to ensure accuracy in the discharge relationship, because we are depending on that stage discharge relationship for converting the stage into discharge. So, obviously, that stage discharge relationship has to remain true for a given period of time where we want to use. For example, here for a particular rating curve in Twin Springs, these two phases stage discharge relationship is shown. So, between 1965 and 2005, this is the blue color, wherein between 1911 and 1964 the pink color. So, as you can see here, there is a change in stage level relation. So, if you continue to use the same old stage level recorder, so for same stage you will be getting much difficult. So, for example, if stage is 6 and you are using the old rating curve, then your flow will be very close to 6000 cubic feet per second. wherein if you are using the new one, then your flow will be only 3000. So obviously, as you can see, there is a just 100% change in the stream flow because of the change in the characteristics of the rating curve. So that is why it is important that we continuously monitor the developed rating curve, and we keep on recalibrating that in order to see that stream cross section remains true. And then we come to area velocity method. And the area velocity method of stream flow measurement provides a practical way to estimate stream flow. It involves measuring flow velocity at different sections of the stream and then multiplying with the cross-sectional area to determine stream flow. So, it is also a two-stage process. We measure velocity and then we determine the cross-section and multiply cross-section with the velocity to get the stream flow. It is practically useful for rivers and streams where the flow conditions vary across the channel. So, obviously, you can understand by looking at the velocity distribution in different types of channels. So, as you can see here, the velocity distribution changes drastically, and that is why we cannot have just a single measurement of velocity at one section. We have to have because if you consider this kind of thing, so if you measure velocity here and the cross section here, probably you will get a wrong picture because velocities of flow are very different at different sections. So, that is why we make several measurements or measure flow velocity at different sections of the stream and then multiply that with the cross section in order to get the stream flow, correct value of stream flow. Now, this area velocity method has certain assumptions behind it, that it assumes that the flow is steady, that is the flow is constant over the time. Over the time during the experimentation, there is no change in the flow. Then the flow is uniform, that is flow is uniform across the entire cross section of the stream. So, you have a cross section of the stream. So, flow does not vary from one section to the other. Then constant channel shape, the stream shape is constant over the section where the measurement is taking place. So, that means there is no sudden changes in the cross section. Negligible backwater effect, that is backwater effects due to obstruction or changes in channel slope downstream are negligible. So, that is why if there is a say a dam or some kind of obstruction just downstream or upstream, then obviously the flow patterns will be very different at a given cross section. So, we assume that there is a negligible backwater effect and there is a negligible side contraction or expansion effects, that is the lateral contractions or expansions on the channel do not affect the channel flow. So, that means if there are any contraction or expansion at the sides, that will not affect the flow. That is, these are the kind of assumptions we make here. Now, coming to measurement of velocity, typically equipment called current meter is most commonly used for measuring the velocity of flow in a stream. Typically, a current meter consists of plastic or metal conical cups or propeller, which are submerged to a point in a stream, and then thus we measure the velocity. And the conical cups or propeller rotate at a rate proportional to the velocity of water, and the flow velocity is determined by clocking the rate of their rotation. So, current meter has either conical cups or propeller. It is immersed into the water, and because of the flow velocity, the either conical cups or propeller, they rotate, and we simply measure the rotation, and from there we determine the flow velocity. That is the simple procedure which we use. Now, Robert Hooke was in 1963 invented a propeller type current meter for traversing the distance covered by ships. So, the first current meter was developed way back in 1663, that means almost 450 years or 460 years back. And later on, Henry in 1868 invented a cup type current meter with the electrical make and break mechanism. So, if we talk about the propeller type, which is here, or a a cup type of current meter. They came into existence long back, 450 years almost in case of propeller type, and almost 250 years in case of the cup type current meters. And current meters are mainly of two types: vertical axis current meters and horizontal axis current meters. And of course, when we come to discuss this, you will realize that basically these are the two types of current meters we are talking when we talk about vertical axis meters or the horizontal axis meters. Coming to vertical axis meters, these consist of a series of conical cups mounted around a vertical axis. So, as you can see here, there is a vertical axis here, and you have a series of conical cups or cup assembly. The cups rotate in horizontal plane, and the revolutions of the cup assembly are recorded through the electrical make and break mechanism. So, here there is a electrical connection and the counting mechanism, and then this rotation is recorded. Sounding weights are used for sinking the meter suspended on a cable. So, as you see, this sounding weight is lowered for sinking this current meter, and also to keep it stable vertically, and in order to keep it stable horizontally, there is a stabilizing fin on the other side. And such current meters are well suited for velocity in the range of 0.15 to 4 meter per second, and Price type and Pigney type current meters are examples of the vertical axis current meter. That means they have these conical cups mounted around a vertical axis. Then the other category, we have horizontal axis meters. These consist of a propeller mounted at the end of horizontal shaft. So, obviously, as we discussed earlier, the vertical axis meters have conical cups, wherein the horizontal axis meters we have propeller type. They are propeller type at the end of horizontal shaft. Due to axial symmetry with the flow direction, these meters disturb the flow less compared to the vertical axis meter. So, in this case, as you saw, if you look at the design of the two, here there is a significant component which might disturb the flow, wherein it is just a propeller which rotates. Also, these are less sensitive to vertical velocity component, because there is no, there is no vertical disturbance. So, there is no vertical velocity component in this case. And these also perform well in the velocity range of 0.15 to 4 meter per second. That means, as far as velocity range is concerned, both vertical and horizontal axis current meters, they are similar in nature. And the typical examples of horizontal axis current meters are the odd type, the Naprick type, or the Hoff type of current meters, and they originate from different countries. Like Odd comes from Germany basically. And the number of revolutions of cup assembly or the propeller is recorded while measuring flow velocity with current meters. So, basically, as we discussed this earlier, that basically we measure the number of revolutions, and each current meter comes up with a unique relationship to convert the number of revolutions into flow velocity. And the relationship between velocity of water and the number of revolutions per unit of time for various velocities is determined for each instrument by experiments, and basically it is provided by the manufacturer. So, typically when we buy a current meter, it comes with a relationship of this form: V equals to A n plus B, where V is the stream velocity at the instrument location, N is the number of revolution per second of meter, and A and B are constants of the meter provided by the manufacturer. So, that simply means when we insert or immerse this current meter into stream, this is what N we measure, and A and B are the constants of the meter that is provided by the manufacturer. So, we can simply convert the number of revolution into velocity in which we are interested in. Now, at a cross section in a stream, basically we have seen that across the cross section velocity varies, but also if you take a vertical cross section, then velocity varies significantly from top to the bottom. The maximum flow velocity occurs somewhere near to the surface, and surface velocity is lower due to friction between the water and air or the surface, and the flow velocity is lowest near the channel bed because of the drag, etc. The friction and the drag, the lowest velocity at the bottom, and though with this graph it appears that the velocity is highest at the top, but it is not so because of the resistance. It is slightly below the surface where the velocity is highest. So, that is why we have to be careful where we measure, at what depth we measure the velocity. So, in shallow streams having less than 3 meter depth, the velocity is measured at 0.6 d times the depth of flow below the water surface. That is, for example, if this is the total depth d, then from top we measure 0.6 d, that is this point here, that is where we measure the velocity. And for streams having a deep depth between 3 to 6 meters, that is slightly deeper ones, velocity is measured at two locations, at 0.2 and 0.8 d, and the average of these velocities is considered the average velocity. So, if it is a deeper stream, then we make two measurements, one is 0.2, one at 0.8 d, and 0.8 d, and then we take the average of these two. So, we have to be careful that if it is up to 3 meters depth stream, then we use 6/10 rule, but if it is between more than 3 meters, then we make measurements at 2 points, 0.2 d and 0.8 d, and take the average of the velocity as the mean velocity of the stream. Now, measuring velocity of in a large stream also challenging, and basically this also can be done through current meters, but in that case we basically use a ropeway, which offer a practical means of measuring velocity in large streams, allowing for the assessment of flow characteristics at different points and depth across the stream width. So, basically as you can see that there is a cableway, a ropeway, and a cable which may carry a person, or it could be automated also, and then streams at different locations which are already known or prefixed points. The current meter, as you can see, the current meter is lowered, and then the velocity is measured at different cross section, across the cross section of the large streams, and then knowing the area we can find out the stream flow. So, here in this lecture we have started looking at various methods of stream flow measurement, and as I said that we will continue because we saw that there are various direct and indirect ways of estimating or measuring stream flow. So, we will continue to discuss in the next lectures also. So, with this thank you very much. Please give your feedback and also raise questions or doubts which can be answered on the forum. Thank you very much.